Welcome to part 4 of Mosfet fundamentals. In this video, I'm going to look at a circuit example with a Mosfet device in, and this is the NMOS device. Assuming we're given a circuit like this, where VGS, positive VGS is applied on the gate, VDD is applied, we have a resistor RD, and you know there's going to be some current ID going down, VDS positive negative because it's an NMOS, and then from there RS over at this point. What is going to happen now is that we're going to actually derive an output, and we're going to derive like a DC transfer characteristics of this circuit. The characteristics change with respect to whatever kind of a circuit that may be, but then like for this circuit, we're going to actually derive, and this is like the basic MOSFET circuit. Okay. So, in the previous video, I explained that and showed on the graph that the relationship between VGS and ID is exponential. But with a small change of VGS with respect to ID, we can approximate a linear change. And that linear change can only be discussed whenever we talk about change in VGS, which can be an input in VGS. Right. VTN is a threshold voltage, and Kn is a physical parameter, and physical parameter controlled by the width and the length of the transistor gate. Okay, so now let's look at the circuit. So now we are going to use the Kirchhoff's voltage law to derive the equation that's going to describe the dynamic change of the system. So let's take some of voltages in this loop, in the DS loop. Now VDD, which now, because like it's up there, it's going to be negative VDD. Now here's the equation I'm talking about at the moment. So negative VDD plus RD times ID. From Ohm's law, we know that like the voltage in a resistor is equal to R, means the resistance of the resistor multiplied by the current flowing in the resistor. So RD gives you the resistance, plus VDS, which is the voltage at the drain to source. This is the drain to source voltage, it's positive. Then plus RS multiplied by ID, so same current flows also at this point, and then ground. So all of this is equal to 0. So what this means is that sum of voltages in a loop must be equal to 0. This is Kirchhoff's voltage law, or this can be looked at as the loop analysis or the mesh analysis. Yes. Okay. So now from here, we're going to make ID the subject of the formula, and when we look at the final formula, we see that the relationship between VDS and ID is linear. So we have a linear relationship between VDS and ID. Now, what changes ID? Okay, because now we're going to look at this, and we're going to bias this, right, at a specific point. Now, if we keep VGS constant, this is like a DC value, VGS constant, and then we actually like connect the specific VG supply voltage to the gate, we're going to get a specific ID. Now that ID is going to actually bias this at a specific voltage. It will like will have a specific ID voltage flowing here, and the ID is not controlled by VDD at the moment, it's controlled by VG. So VG will allow a specific amount of ID to flow in the drain to source loop, and from there, depending on the value of VDS, we're going to also have a variation in ID. So basically, VDS is the voltage that is here. Okay. Now, let's look at a situation where there's going to be a change in VGS. In the previous video, I looked at the change, but then explaining biasing of a transistor. Let's look at a change. Let's assume that like we are putting a voltage source here. Let's assume that like we plug in a voltage source. Yeah. And that voltage source is not like a DC voltage. It's an AC voltage. Let's assume that like we actually place an AC source here. Let's say we place an AC source here. Now, if we plug an AC source here, there's going to be a change in VGS. Now, this VGS represents like a voltage source. Okay, fine. This circuit is not drawn to scale. Okay, and at the same time there must be a voltage source here. There must be a DC source here. Okay, which is positive and negative. Okay, so there must be like a positive to negative, and from there you're gonna have an AC voltage here. So we know that like two voltage sources connected in series actually add up, and the voltage we'll see here is going to be the stable DC voltage plus an AC voltage. So this AC voltage can be any voltage variation from as little as 1 millivolts to any voltage. Okay, now let's look at this line. Now, when we actually have this, we can say, okay, fine, we are biasing this thing, okay, like, let's look at this loop, okay, fine, before I actually look at the change of AC, let's say we have this loop equation here, and then we've got VDS here. That means basically we bias the transistor at a specific VDS, okay. If you can bias the transistor at a specific VDS here, now we'll have a specific VDS. Now let's look at this graph. We'll have a specific VDS here. Just like in the previous videos, we had a specific, we had this transfer table. So now we're going to have a specific VDS over here. Now, this will also be linked to a specific VGS. Now, as VGS changes, it's going to change ID. In this case, we're going to look at a sinusoidal change of VDS, assuming that like we're actually plugging in a sinusoidal change. That means we're plugging in a trigonometrically like changing sine wave, and by trigonometrically I'm talking about sinusoidal, and sinusoidal I'm talking about either it's a cos or a sine wave, not a tan wave. Sinusoidal just means oscillatory in a smooth path or a smooth trajectory. Now, assuming that now VGS changes, let's look at this and based on the value of VDS describe at what point can VGS change and allow a beautiful change in VDS. So VGS is linked to ID, VDS is linked to ID. Okay, but then this graph actually shows us, okay, for the relationship between ID and VDS based on this equation, and it also shows us the characteristics of the transistor and also our VGS and ID relationship. So but at this moment, we're going to look at, okay, fine, the DC bias. This thing just means that our DC is biased at this point, meaning our VDS DC is at this point, and then also at that current. And then from there, we have a specific VG. Now, when we shake VG like that, this thing will stay in saturation. It will stay in saturation and will remain almost linear and will change ID almost linearly. Okay, but it won't be like that forever. Don't forget, as VGS changes ID, and ID changes VDS. So when ID increases, because of the change of VGS, when VGS increases and ID increases, our VDS will decrease on this trajectory and hit this point. Concurrently, as VGS decreases, it will decrease ID, and that will increase our VDS. Don't forget now, the reason why our VDS is increasing is because like the current is decreasing in this line, and as the current in this line decreases, there's going to be less voltage dissipation in these resistors. And if there's less dissipation of voltages in these resistors, what will consume most of the voltage will be the resistor. So basically what happens is that now as the current decreases, the voltage in VDS increases. So as the current decreases, the voltage in VDS increases. Now, at some point, this trajectory hits specific bounds. We can see at this point it hits VCC, which is the supply voltage, and at this point it hits the link between like our triode mode and our saturation mode. So at these 2 points, we can see that, oh, okay, fine, we are hitting like the rails. Okay. We are hitting the rails. Now what happens is that we can divide this into 3 pieces and say, okay, fine, here we've got our bias point and we've got our saturation point. We have a saturation point here. Okay, so this actually tells us a little bit more about our circuit. It's okay, fine. Our circuit change in ID looks almost linear because of the change of VGS linearity down there. And then also now the relationship between ID and VDS is linear because of the of the DS loops equation like on the side. Like following on that, you also see that, okay, fine, as VGS changes, ID will change and that will influence VDS, and then the circuit will operate on this line, and this line slope depends on the resistor and the resistance values, the resistor values, basically. So because like, I mean, if you look at this, this whole line, this whole line is a function of ID with respect to VDS, and VDS is part of this equation. And if you look at this, you can separate this two. You can actually remove the RD plus RS and make it like basically you can have like VDD over RD plus RS minus VDS over RD plus RS. So meaning since VDS is actually our changing variable, now the slope is 1 over RD plus RS. So the slope changes from this. Okay, so this slope is actually 1 over RD RS. So as VGS changes, it's going to increase the value of this and decrease the value of that, and then give us the resulting things. Now from there, we can see that the distance between these two is not the same. The distance between these two is not the same. The distance from here to there, and the distance from here to there is not the same. So if ever you are dealing with like voltages that are changing, and you ever asked to compute like the maximum swing that will have less distortion, basically that means a maximum output swing that is equal, that will give you less distortion. What you should be looking at is the smallest, because if you want it to be equal and you want it to be distortionless, that means basically you must actually operate on this one. I mean, this on the left and the right is going to be your maximum voltage, meaning you want to oscillate around this point. You want to oscillate around this point. You want to oscillate around this point. Okay. You want to oscillate around the point like this. You want to oscillate around this point. Okay. Okay. So basically it means that, well, you want to work around this point. So it means you want to oscillate around this point. So this just means that, okay, fine, we have a center point, and the center point is our bias point. Center point is our bias point. So you can actually go from here up to that point, which is saturation, and you can go from here, which is that point, which is actually our VDS value, whatever VDS value that is. But that VDS value is equal to our VDS saturation value on the side, which cut our thing short in this instance. Okay, so that's going to be our maximum swing from here to there.